In example 2, we're going to still be somewhat in warm-up mode. So here I would like you to just think about how you would split these up. We're not going to go all the way through how you find the values of the constants and things involved, but I want you to look at this and say, okay, if I'd split it up, I'd need 2 fractions, or I'd need 3 fractions, or whatever, and the denominators would be what? So really key to this is always going to be getting these as factored as possible. So that one factors into an x minus 3x plus 2. And then the question we're asking ourselves is, if that's the least common denominator of some simpler fractions, what denominators could have appeared among those simpler fractions? And the answer for this is we don't have a lot of choices. These are the easiest ones. There had to be an x minus 3 and there had to be an x plus 2, and there can't really be anything else, or we'd have more stuff in our LCD, and neither one can be missing, or we wouldn't have both factors in our LCD. The next question you need to ask yourself is, if we're going to end up with a reduced fraction, so we know that the degrees of our numerators can't be bigger than the degrees of our denominators, but we don't want to lose any possible things that could have shown up, meaning we don't want the degrees to be too small, then what could we have? And here we don't really have a choice, because the degree of the bottom is 1, which means the degree of the top has to be 0, which means they have to be just a constant. And you can pick your letters, it doesn't matter. I generally just do capitals and start at A and start working my way through, but that's not a rule. As long as you don't use the variable x that's already in this problem, you should be in good shape. So that is the partial fractions decomposition for this problem. In number 3, we'll work on how you actually find the values of a and b, but in this one, I just want you to have an example to look back at as to how we break these down. The second one, the x squared plus 1, that's one of those irreducible quadratics. You cannot factor that further. You're stuck with a quadratic. You'll have to compensate for that when you split this up. Okay, so x squared minus 6x plus 9, that does factor a little more. That factors to x minus 3x minus 3. So this is an interesting one because we have a repeated factor with that square on it, and we have an irreducible quadratic. Okay, so again, if you haven't, pause, try to do this one before you watch. It's really important that you try this, and then you can look back and see what went wrong. If anything, hopefully nothing went wrong. So with the repeated factors, the only way we'd have an x minus 3 squared in our LCD is if we started with an x minus 3 squared. And then we have to allow the possibility that there was also an x minus 3 to the first power. That doesn't need parentheses. If we had both of those, to get a common denominator, we'd multiply the second fraction top and bottom by x minus 3. And that would give us our x minus 3 squared still as our common denominator. This one's a little funny because the first factor is quadratic, so people want to think about it as this should have a linear numerator, but it's a repeated factor, so it actually only gets a constant. And I'll show you why. Because if you went to add these together, so kind of side note, we would do what I was just talking about. We would multiply this one top and bottom by x minus 3. And when we add that up, we're going to get a plus bx minus 3b all over x minus 3 squared. And that gives us our linear, our first degree. So this is still second degree. This is now first degree. That does give us our linear numerator. So the only reason that we don't have to have a first degree where I put the a is because when we add those two together, it takes care of that for us. So we're always trying to get the simplest pieces possible. So it actually wouldn't be wrong to say this is ax plus b. But then you don't have the simplest pieces possible, and that's still not that easy to integrate. So we can do even better if we split it out into a second fraction and say the x part comes into play when we add them back together. Okay, and then the irreducible quadratic, the x squared plus 1, That one is a little trickier. We can't split off a second fraction with a different denominator that would allow it to be linear. So this would be cx plus d. My advice, that's fine just like that, but for integration purposes, my advice is to split that up into two fractions as well. They have the exact same denominators. That's why we do have to have the x there, because when we add them up, we're not multiplying by any variable stuff to build up the power of the top. But you can split them out into two fractions, and then notice that when we integrate that, we should get some sort of arctan. When we integrate that, we should do a u substitution. W substitution. And this guy would end up being some kind of natural log. And this one, we would do a power rule. That's in stuff to the negative 2. So we should get stuff to the negative 1 divided by negative 1. So that's kind of a common setup, that you'll have some linear factors, maybe a repeated linear factor even, and then some irreducible quadratics that you can split into two. So again, you're not wrong if you combine these into one, but at some point you're probably going to have to split them apart to integrate. So my advice would be just to do that from the beginning so that you don't miss it later on. Okay, third one, we can factor a little more. We can factor out an x cubed. That leaves us with an x squared minus 1. And we can do even better than that. We can say that's x cubed times x plus 1 times x minus 1. And then this x squared plus 4 is an irreducible quadratic. It also has a power on it, so that makes it even more interesting. So you probably won't actually have to do partial fractions on something this messy, but just so that you have an example of everything from the last page. To deal with the x cubed, we would have to have the possibility that there was an x cubed, and then we would want to allow for the possibilities that there were also x squareds and x's floating around in the denominator. Okay, so that deals with the first three. We'll talk about numerators in a second. If we have an x plus 1 and x minus 1 in our final fraction, there must have been an x plus 1, x minus 1 in the denominators of the simpler fractions. And then this is a little tricky with the x squared plus 4, since it's a repeated factor. We would have to allow that there was an x squared plus 4 squared and an x squared plus 4 to the first power, which I guess doesn't need parentheses. Okay, so tons of fractions here. Again, you're not going to have to do the actual solving with this many fractions, but just so you have examples of how to split it up. Your next step is to pick out the numerators. Should they be constant? Should they be linear? So remember that the first three are a group, and because of the way they group together, we don't need a quadratic numerator for the x cubed and a linear numerator for the x, and a constant numerator, linear for the x squared and constant for the x. Because when we get a common denominator, the c over x will get multiplied by x squared. There's our quadratic, and then the b over x squared will get multiplied by x's, and there's that linear piece. So putting those three back together would make the quadratic that you might be looking for. Here we have linear, so first degree needs a constant, and e, another first degree which needs a constant. And then these last two are funny. This is the one time when you actually do have to put an x in your numerator if you have an unfactorable quadratic. If you can factor the quadratic, then you can always break off other fractions that would allow you to then beef the numerator up when you put them back together. But if you can't factor it and you can't break them out into simpler fractions, e, f, x plus g, h, x plus I. And these you could split up more. I just knew I was running out of room. So really I would say fx over and g over. And same for the other one. So not wrong to write it as a single fraction, but simpler when you integrate to write it as two fractions, and also it kind of matches up better with what we do for repeated factors, where you can see that the beefing up the power happens if you add them back together. Okay, so there's a messy one. Look back at that if you're not sure what your denominator should look like.